Now that we have proved that even if the original population is not normally distributed, the distribution of sample means from a large number of independent, identically distributed sample approaches a normal distribution, the central limit theorem. Now it's time to check the characteristics of this normal distribution. I have already replaced column A with diastolic blood pressure, back to diastolic blood pressure. If you have some other values, please go back to your hard sheet and then copy diastolic blood pressure and enter it here. Okay, now let's move on to the end of this spreadsheet and see what is the mean, median, and mode of them and if they are all aligned. Okay, so the mean of the sample mean. So it is the mean of the sample mean, right? Sample means. Okay, so because we have like 1,000 sample means here, and it is going to be average of all these values, and we see that it is 85.4. Okay, very close to the unknown population means 85.35. We see that the mean is like 85.47, almost the precise sample population mean, right? Next, let's check the median and see if it is the same as mean. Okay, equals median of this column CZ, parentheses close, and we see that mean and median at least are exactly the same. And now let's check mode. Okay, equals mode of this column, which is very close to 85.28 also. So thus proving that mean, median, and mode of a normal distribution are almost equal. Next, let's check if the empirical rule applies here. Okay, I'm gonna just delete all these columns. We have already confirmed that. Okay, so here is the sample mean. Okay, now the mean of the sample means. Mean of the sample means. We're gonna use the same process which we used previously in chapter 3. We will calculate the z-score, and then we will count how many z-scores are between 1 and -1 and 1 +1, and how many z-scores are between -2 and +2. Okay, and that will show us how many values are between 1 standard deviation and how many values now by percentage are between 2 standard deviations. Okay, the mean of the sample means is equals average of this column, which comes down to be 85.45 as we previously calculated. And if you see, every time we enter a value, all these values keep changing, so which is good, in fact, because it shows that how many of them are because these are randomly selected, and we have a further confirmation that even if all the individuals are changed, as long as the number of individuals in the sample are the same, the mean of the sample means are going to be same. Okay, then the difference for the first sample is E8 minus the mean of the sample means, almost 0.28, and so on. Okay, next I'm going to calculate the standard deviation by formula, which is equals stand div of the means of the sample means, standard deviation of the sample means. Okay, 1.28, and I'm going to enter all these values in the cells below, and so the z-score is the difference divided by the standard deviation. Okay, so it is kind of saying that the first value is 1.7 standard deviations below the mean. Second value is 0.23 standard deviations below the mean. In contrast to saying that first value is 0.2 millimeters of mercury below the mean. Second value is 0.30 millimeters of mercury below the mean. Now we have a standard value here which shows that how many standard deviations each of these values are below or above the mean. Okay. Now I'm going to use the same formula which we used previously. I'm just going to replace the column, copy it. I'm going to come back and check 95% rule here. Okay, I'm going to paste that formula here. I'm just going to replace this GG with DD column. Okay, and I'm going to just replace all of the column G with column DD. Okay, over here to delete this and paste DD and here too. Okay, now we see that all these sample means, which we have already at least visually see that they were normally distributed. Now we have a confirmation of that, at least 95% rule, that of all these values, 95% of them are within 2 standard deviations, right? And if you want to check 68% rule, we're going to replace this formula. We're going to use the same formula here. Okay, only that we are checking 1 standard deviation below or above the mean. Okay, and we see that it's very close to 68. And now if we keep replacing all these values with any other variable, maybe weight, go back and replace, as we previously saw, that although the normal population, well, in this case it is quite normally distributed, but we see that the means of the sample means is very normally distributed, very close to the, and we see that the values within 2 standard deviations are almost 95% of them, and the values within 1 standard deviation are almost 68% of them. Even with smoking, which is totally not normally distributed, as you can see on the left histogram, their means are normally distributed. Means of the sample means are normally distributed. Still, we see that 95% of these values are within 2 standard deviations, and almost 68% of these values are within 1 standard deviation. So in fact, the message over here is that whenever you take a sample which is large enough, normally we take the values 30, which a sample of 30 or more, we are going to have a sample mean which is going to be in 95% cases within 2 standard deviations, right? So I repeat, even if you take any of these samples, you have 95% probability of within 2 standard deviations. So remember this law, and then we will learn more about that to show that how we calculate the mean of the whole population based on just 1 sample. Okay.